Hello everyone, I'm Mingji. Today I'm going to present ByteCheckpoint, a unified checkpoint system for large foundation model. This work is a joint work of the ByteDance seed and the University of Hong Kong. In recent years, large foundation model in language, vision, and audio and other modalities evolve fast, spurring a variation of downstream applications such as chatbot, coding assistant, painting tools, and video generator. If we take a look at the large foundation model training cycle, checkpoints plays a key role in the full large foundation model training cycle. During the training system saves checkpoints periodically. When the software or hardware failure happened, training system resumes from the latest checkpoint to reduce the loss of the training process. The checkpoint is also used in evaluation and the cross-training stage transfer. In distributed large language model training states is sharded on multiple GPUs because of different parallelism methods such as tensor parallelism or pipeline parallelism. A checkpoint consists of 4 parts: model, optimizer, data loader states, and actual states. In order to build a checkpoint system for the efficiency and effectiveness of large foundation model training, there are 3 requirements for that. The first is load time resharding. Before we talk about resharding, we need to specify what is the checkpoint resharding. In the foundation model training, the training system may save the checkpoint in one parallelism setting, and it may need to load it in another parallelism setting. For example, we save the checkpoints with 16 GPUs, then we want to load it in 32 GPUs. Checkpointing resharding means that you transferring distributed checkpoints so they can be correctly loaded into another new parallelism configuration. In industrial training, there are many cases we need to change the parallelism setting for training, and you need to do the checkpoint resharding. For example, the GPU resources is dynamic. The number of the GPUs available for a specific training task changes. We may need to increase or decrease the number of GPUs for training. For example, you are training a large foundation model with 5,000 GPUs, then another task is finished. There is another 5,000 GPUs available. You want to scale your training by doubling your GPUs. Even the GPU resources is fixed, we may need to change the parallelism setting to tune performance, such as tensor parallel size, expert parallel size, or pipeline parallel size. When we change the training stage, the training parallelism setting is likely to be changed. For example, we do pre-training with 1,000 GPUs, but we only use 100 GPUs for supervised fine-tuning. The same thing also applies to evaluation. The number of GPUs for evaluation is much less than pre-training. A common practice for checkpoint resharding is using offline scripts. However, our experience shows that this is a terrible solution. Here is an illustration of how to use this script. You need to specify the parallelism setting, model structures, and different checkpoint model name. So we found that it is very hard to develop it because resharding logics is highly coupled with the training framework, model structure, and the parallelism setting. And another thing is that when we're running the offline scripts, we need to wait until the resharding procedure finished, then we can start another training task with new GPU resources, which is a great waste of the GPU resources. Sometimes for large training tasks, it takes 4 or even more hours to reshard a checkpoint. In ByteDance training platform, we use multiple training frameworks based on the training task, model size, or training skills. We observe that they have the similar functionality requirements regarding the checkpoints. Building checkpoint models in different training frameworks could bring significant engineering efforts. So if we can have a unified checkpoints could support all the training frameworks, it could be very helpful for code reuse and reduce the maintenance cost. The last requirement is that we need efficient and scalable I/O. In industrial, training large foundation model needs a lot of GPU resources, and the model often contains billions, 100 billions levels parameters, which brings large checkpoint states. For example, Meta trains Llama 3.1 405 billion model over the 16,000 GPUs. If training system saves the checkpoint synchronously, it blocks training for a long time, leading to a great waste of GPU resources. So the efficiency of the saving and loading checkpoints is crucial to training efficiency. There are also some challenges can only be found when doing the checkpointing with more than 1,000 GPUs, for example, file system bottleneck and collective communication bottleneck. To meet the checkpoint demands for ByteDance large foundation model training, we built ByteCheckpoint. In the API layer, we provide simple and easy-to-use API like torch load and save. Users don't need to take out details of distributed checkpoint. The planner layer is responsible for coordinating all ranks to generate the saving, loading checkpoint plans, and the global checkpoint metadata. Execution engine is responsible for running, saving, and loading I/O operations and manage I/O resources based on the given saving and loading plans. Storage layer is responsible for interact with multiple file systems to load and save checkpoint file and do the actual I/O operations. Next, we will introduce how to achieve automatic load time checkpoint resharding by designing a parallelism-agnostic and decoupled checkpoint storage representation. A ByteCheckpoint storage file consists of two parts, the data and the metadata. Unlike the offline resharding, which directly generate new checkpoint files, ByteCheckpoints leverage this design to use the metadata to locate and read the corresponding slides of each tensor during the load process. This enables the resharding to be performed automatically at the start of the training. Here is an example of tensor data and metadata. The data stores actual tensor in bytes. The metadata records the key information about tensors, including the key name, sharded specification, file offsites, and the length. Based on the metadata, we can do the load time checkpoint resharding instead of using the offline scripts. Here's a living example. When checkpoint resharding happened, ByteCheckpoints could find matches between the runtime tensor sharding specification and the tensor metadata in the checkpoints. Then the training system could load the tensor shards based on the new parallelism setting according to the metadata. We also build representation for data loader and actual states, which are essentials for resuming training states from checkpoint correctly. In addition to tensor resharding, data loader resharding is also critical because in the distributed training, data loader prefetches the data from the remote file systems and maintains token buffers in memory, which are also persistent in checkpoints. When changing the parallelism setting, ByteCheckpoints reshard the data loader states according to the parallelism setting chains to avoid the loss of training data. For the best saving and loading performance, we build fully asynchronous saving and loading pipelines and optimize each stage fine-grainedly. For distributed checkpoint plan generation, we use tool optimization, which improves the saving performance significantly. The first is load balancing, because in the data parallel training models are replicates on different DP process groups, so we can do the load balancing, let all DPs save the parts of the models. The second optimization is plan and metadata caching. Doing a training, the model structure and the parallelism is fixed. So once we generate a saving or loading plan, we can reuse it during the training cycle without do the collective communication all the times when you save checkpoints. In the distributed planning, we use the all-gather and broadcast to avoid peer-to-peer communication because, for example, when we do the save planning, we want to gather the local save plan from all ranks to the rank 0. However, if we use the gather or scatter those P2P operations, it allocates much buffers and lead to the out of memory at large scale training. So we use the all gather and the broadcast as the alternative to the gather and scatter, because this is a ring communication. You always allocate too much buffer on rank 0. Hierarchy gather scatter further reduce the connection, establish overhead, and improve the communication stability in large-scale training. Taking the 3D parallelism as an example, it follows the 3D level tree structure across the tensor parallelism, data parallelism, and pipeline parallelism process group. In this way, rank 0 will not connect to the all remaining ranks at the same time, which address the problem of the P2P communication. For large-scale industrial training, system observability always plays an important role for the performance analysis and fault diagnosis. We build a visualization for checkpoint performance analysis. Here is an overview of our visualization system. In the left figure, you can see the topological performance overview. You can have an overall checkpoint performance for all GPU's processes. And in the right figure, you can analyze a single process checkpoint performance by zooming in and time breakdown. We evaluate our system performance with variation model and hardwares and compare the baseline with the open source state-of-the-art distributed checkpoint system like PyTorch distributed checkpoint and Megatron distributed checkpoint system. And ByteCheckpoints demonstrate that we have greatly reduced the runtime stores and end-to-end checkpoint saving time. The checkpoint loading and resharding time is also significantly improved compared with the baseline distribution. Especially, you don't need resharding script anymore. We also need to ensure the correctness of the checkpoint resuming. We verify the correctness of the system by measuring the loss and data loader sequence length before and after the loading checkpoint. When training at the super scale, for example, we're training with about 10,000 GPUs. ByteCheckpoints only blocks the training for seconds when saving checkpoints. In conclusion, ByteCheckpoints is a unified checkpoint system with highly optimized I/O performance and functionality. ByteCheckpoints has been widely deployed in ByteDance seed, supporting large foundation model developments, including text model or visual language model. Our source code is available on GitHub. Thank you.